Hi guys, today we're going to learn about parametric surfaces and their areas. Recall from previous sections that we learned how to find the area of a region D that lies in one of the coordinate planes using a double integral. So back in the day what you learned, it was that the area it was going to be equal to the double integral of this D 1dA. Okay, now what we want to define is going to be the surface area of a general parametric surface. Okay, so the first idea that you need to take in mind is that we're going to have a vector value function like this, okay, parametrically defined with two parameters u and b. So you're going to have your x, your y, and your z components. Okay, so for simplicity what we're going to do is we start considering a surface S whose parameter domain D is a rectangle. So you have a situation that looks like this, and we're going to divide this big rectangle that you can see here, okay, into sub-rectangles. So let's look at this rectangle that you have over here, this one, that it's technically speaking is the sub-rectangle R sub ij. Okay, let's choose specifically speaking this point that you have here, that it's going to be u sub I star b sub j star. Okay, so it's going to be this one that you see here, okay, and this is u and this is b. Please note that this is parameterized. So if you use the vector value function, okay, you are going to choose u sub I star comma v sub j star to be the lower left corner of this one. Okay, so this one that you see here. So when we transform this into a 3D, this is a 2D figure. When you transform this into a 2D figure, because that's where we want to end up, you are going to have that point that we have here is this one that you see over here. So as you can see, this one, this square that you have here is a representative square, is going to be that S sub ij that we have over here. Okay, so the part of S sub ij of the surface S, it's going to be corresponding to this rectangle that we have in the situation in 2D. So this is called a patch. So if you imagine if you have a quilt, okay, so it's one of the pieces, okay, of that quilt, okay, and this one has the point P sub ij, the one that you have here. So you are just moving, let's say that you are moving the quilt, okay, so with the position vector R of sub I star comma v sub j star as one of the corners, which is this one. Okay, so what you have is as we did before, okay, you're going to find the partial derivative with respect to u of the r star. Okay, so and then you're going to find the partial derivative with respect to v of the r star. Okay, so these are going to be the tangent vectors at p sub ij. Okay, so this is going to be pretty much the patch that you have if you maximize and you zoom into the situation. So this is the patch that we have here. Okay, so the p sub ij is going to be also over here, right? This is going to be your point. Okay, recall that the tangent plane is going to be useful in approximating, okay, the surfaces, and we also know the area of the parallelogram is determined by this is at the very beginning of the school year. We learned that the cross product of the vector A cross B, okay, the magnitude is going to give you the area of that parallelogram. Okay, so this looks like a parallelogram, so it's great. Okay, so you are going to approximate the area of the patch with the parallelogram determined by the tangent vectors. Okay, so that's why we want the two tangent vectors, this one and this one. Okay, so what's the surface area? Let's look at the definition. If you have a smooth parametric surface S, okay, and you have that that's given by the equation R of uv, that's going to be equal to some x component, comma, y component, z component. All these components have two parameters, u and b, okay, with u and b being on D, okay, and S is covered just once as uv ranges throughout the parameter domain D. Then the surface area of S is going to be, the area is going to be equal to the double integral of D. Okay, then you have the magnitude of the cross product of R partial U cross R partial B of dA. Okay, where you know that the partial derivative of R is going to be each one of the components, the partial derivative with respect to U. Okay, and similarly with the partial derivative of R with respect to b. I will code that. So let's look at some examples, and you'll see that it's pretty simple. Okay. For this example, what we have is to find the surface area of the part of the plane 4x plus 2y plus z equals 8 that lies on the first octant. So this is giving you a lot of information. So you know that that's going to be, technically speaking, kind of like the first quadrant, okay, for 2D but for 3D, okay? So from that you can see that z is going to be equal to 8 minus 4x minus 2y. So the first thing that I would do here, and let's do it like this, step 1, I would parameterize my situation, okay? So you have that this vector value function is going to be with x and y, okay? So as you can see, I'm going to leave my x alone, my y alone, and my z is going to be depending on x and y. So you have a situation like this, okay? So then you take the derivative with respect to x, okay, the partial derivative with respect to x of your vector value function, which you know that it's going to be what? 1, 0, negative 4. And then the partial derivative with respect to y of this vector value function is going to be 0, then you have that it's going to be 1, and then you have that it's negative 2, okay? So now, as we were doing before, you can see that we're going to do the cross product here, okay? So you're going to do r sub x cross r sub y, so you know that this is going to be your ijk, and then you're going to have 1, 0, negative 4, and then 0, 1, negative 2. Okay, you can do the cross product in the calculator manually. These are constants, so it's pretty simple. So you have that it's going to be 4, 2, 1. Okay, so this is going to be your cross product. Now that you are here, you can see, let's look at the graph, okay? So since we're talking about the first octant, okay, in this way, in 2D, we're talking about quadrant 1, okay? So this is what we have. You have that this is going to be x and this is going to be y, because we're working with x and y in this situation, okay? So technically speaking, what you have here, okay, you do have that y is going to be equal to y into d. You have that y is going to be equal to negative 2x plus 4, because you can see that the intersects, what are going to be the intersects for x and y? You know that for the y is going to be what? It's going to be 4, okay? And then for the x is going to be 2, okay? So please remember, this is not proportional, but it's so you can see what's the business here. Okay, so the area that we're interested is this one. This is what we call D, okay? So, and you can see that this comes from here and here and this one, right? So you can see the intersects here, okay? So step 2, okay, what I call step 2, so you can have it organized. You actually find the area, right? So what's going to be the area? As you know, the formula tells you that it's going to be the double integral of this region D, and the formula per se, it gives you that it's going to be the magnitude, right, or the norm of this cross product dA, okay? So that you have it, that it's a formula. So nicely, we know that we can compute this, okay? So you do know that it's going to be what's going to be the magnitude of that. That's going to be root 21, okay? Why root 21? Because you know that this is going to be 16 plus 4 plus 1, that's going to be 21, and it's the square root, right? So you know that you're going to find the magnitude of this guy, okay? Then you have your dA, okay, as it is. Now here, as you know, we're working with x and y, so what are we going to do here? Honestly, I would do dy dx. You know that it's my favorite in this equation. So let's set it up like that. So you have that it's root 21, and I would do dy dx because we're more used to do that, okay? What's the top? The top is going to be the equation, that linear equation that you have, negative 2x plus 4. That's going to be your upper limit of integration, and then the bottom of that situation is going to be 0. Then with the y, the x, excuse me, that's your y, right? So for the x, you know that it's going to be from 0 to 2, and then I would type this in your calculator, okay, and you would have that it's 4 root 21. Isn't that nice? So as you can see, not that bad, okay? Following the same idea for the next problem, what do you have here? let's parameterize first. Okay, so I would always parameterize first. So you have find the surface area, the part of the plane z equals 4 minus y that lies within the cylinder, x squared plus y squared equals 1. Okay, so they are already warning you that it's a cylinder. Therefore, what I would do here, I would do again xy, since your cylinder is basically with x's and y's. So you have the x, the y here, so as you can see everything is nice, and then you can see that the z is going to be 4 minus y. Okay, so you see that that is going to be the business with the parameterization. Okay, so similarly as the problem before, you take the partial derivative with respect to x. So what do you have here? You have a 1 0 0, which is super nice, and then you have the partial with respect to y of this one. What do you have here? That it's 0 1 negative 1. Beautiful. Okay, similarly to the previous example, you do the cross product. Remember, the partial with respect to x goes first, so you have this one, then you have ijk 1 0 0, and then you have 0 1 negative 1. Okay, you do your cross product. Remember, this one actually it's pretty easy to do it by hand, so you do that, it's 0 1 1, which is a super nice vector. Again, find the magnitude of that one. That's going to be the magnitude of this one is going to be root 2. Okay, so in step 2, what are we going to do? We're going to apply the formula for the area of the surface, okay, for a parametric, and you do know that I'm not going to repeat the formula because you already know that it's going to be the magnitude of this one, okay, which is root 2 dA. Okay, now you're going to tell me what in the world I'm going to do. Again, look at this guy. What do you have here? Okay, so because we are done with the plane z, right? So you are in xy again. Always go back to your basics. Okay, so let me get this, and give me 1 second because you know that I'm horrible doing circles, so it's better if we do it pretty here. So let's do our circle very pretty here. Okay, and even with that, I'm horrible doing circles. Look at that. Okay, so you have your circle here. So you have that this is going to be 1 1, this is going to be negative 1, and this is negative 1. So you have all this area, right, that is going to be your super D. Okay, so now this one, as you can see, it's screaming polars, right? Why it's screaming polars? Are you going to work with horrendous square roots here? Because you can simplify as y equals plus minus, and then you have the 1 minus x squared. But honestly, the integration bounds are going to be horrendous. Therefore, I'm going to use polars. Okay, so this is screaming polars. Remember that when we do polars for double integrals, what are you going to do? Okay, so you're going to do this guy, and your dA is going to be dr d theta dr. Okay, so let's look at first the limits of integration based on the theta. You know that the theta, since it's a full circle, it's from 0 to 2 pi, and then the r, because it's a circle radius 1, you know that it's from 0 to 1. Okay, which is pretty nice because you can use here Fubini as usual. Okay, so it would be nice. So you don't have any issue. Even with the calculator, I'm just going to plug it in the calculator, and the calculator will give you root 2 pi. Okay, but I would use Fubini, the separate the theta and the r, and then this one is just r, so it would be r squared divided by 2, and this is just a constant. Okay, so you can see where the root 2 comes from and everything. Okay, so it's very nice. Okay, so let's look at the last example of the day. What's the business for the last example of the day? You need to find the area or the part of the surface, and we have y equals x squared plus z squared that lies inside the cylinder. X squared plus z squared equals 2. Okay, so this one we're not be working with x and y as the other ones. Okay, so we need to be a little bit careful. Okay, so let's start with step 1. What's the business for step 1? Step 1, you are going to parameterize. The parameterization of this one is not as trivial. You can see that the y is depending on x and z. Okay, so I'm going to do x comma z. Okay, so you can see that here my vector value function is going to be x comma x squared plus z squared comma, and then you have the z, right? Similarly as the previous ones, I'm going to take the partial derivative with respect to x, which is not bad. It's 1 2x comma 0, and then you have that the partial with respect to z on this one is going to be what? it's going to be 0 to z and then 1. Okay, so again, you do the cross product as exactly as before. Oh, it's a z, you work it exactly the same. Don't worry. Now our 2D visual is going to be different, but that's okay. Okay, so you have this. Okay, this cross product, when you perform it, it gives you 2x minus 1 comma 2z. Okay, that magnitude is not going to be fun. Okay, why? You know that this magnitude is going to be 4x squared, and then you have a 1, and then you have 4z squared. Ugh, ew. Okay, so let's start writing here step 2. Okay, and let me again write your not polar, well, it's going to be polar eventually, well, cylinder, excuse me, cylinder gun. So you have that your circle is going to be this one, but that radius is not going to be 1, right? Even though it's the same size as the other one, you know that this one is going to be what? Root 2, this one is going to be root 2, this one is going to be negative root 2, and this one is going to be negative root 2 as well. Why root 2? Because of that one. So the area that we're looking here, this is your D. Okay, so you can see that again, your area, okay, of the surface is going to be the double integral D, and then you have that it's going to be 4, what was it, x squared plus 1 plus 4z squared, and then you have that all of this dA. Okay, again, this is screaming polars. Okay, so again, I'm going to put here polars. Oh, but we have that this is x and this is z treated the same. Okay, so what you're going to have here, when you convert this to polars, you have that this is d, and then you're going to have that it's 4, and then technically speaking, you have r squared plus 1. Okay, and then you have r d theta dr. Okay, so I would go ahead and erase the d here, and what would you put here? You know that for the theta is going to be 0 to pi, okay, because it's a full circle again, and then it would be from 0 to root 2, because that's basically the radius that you have in this equation. When you plug it in the calculator, you have that this is 13 pi over 3. And that's it for today. I hope that you find this video helpful. Bye!